Good day everyone, my name is Thanh. I'm a PhD student in the UTS Robotics Institute. Today I'm going to present my paper titled Investigating the Effect of Sensor Data Visualization Variances in Virtual Reality. First, I want to introduce and talk about the motivation of this paper. I'm a part of a research team working on HALO, a research collaboration project between Austral, IMCRC, and UTS. The system we are creating aims to assist with rock scaling operations that workers currently do manually. You can see the image of our system on the right. Because robots are not very good at eye-hand coordination and making high-level decisions yet, the system cannot be fully autonomous. So the intermediate and arguably more optimal solutions is to involve humans in the loop. This is where virtual realities comes in, as it allows users to intuitively interact with robot systems. Additionally, in recent years, hardware and software development for virtual reality has enabled researchers to leverage representations of the real world in a virtual environment. However, when rendering data information in VR, several research challenges arise. These include what data to show to the user, or how to effectively represent and transfer information rich and dense data sets to a VR environment in real time, and what influence data limitations have on users' ability to perform manipulation tasks. In this paper, we conduct a user study to determine the ideal configurations for the VR-based control interface. The user study investigates the effect of real-time sensor data variances on humans performing straightforward assembly tasks in VR. Experimental results were collected from 12 participants performing a total of 95 tasks. The tasks require users to manipulate objects using stream sensor data such as point clouds and images in a VR environment. A multi-computer setup was devised to acquire, transmit, and render real-time RGBD sensor data into a VR environment. The data variances interest include the preferred visualization modality, frame rate, color informations, and resolution. The system consists of two machines connected by Ethernet to minimize latency. One machine obtains data from a real-sense camera via a ROS environment. The raw depth and color images received from the camera are compressed before being sent through the network. The second machine receives and processes the sensor data, then renders it into the VR environment. As mentioned, the data is transferred using compressed images. This is to enable real-time data transmission between two computers. Even though an existing ROS packet is used to manipulate the image compressor process, an extra step is required before compressing the raw images. The depth images received from the cameras are encoded in a 16-bit format, which is unconventional for general image compressions. And consequently, two image streams are constructed from the original depth image stream, an upper and lower 8-bit image. The single color and two depth images are then compressed using JPEG with the highest compression quality to minimize data loss, and then transferred to the second computer. After the three images are received on the second computer, the software decompresses the images, reconstructs, and renders the point cloud into the VR environment. The point cloud reconstruction is implemented using a pinhole camera model to convert each pixels of the depth image into a 3D point. By processing the depth image streams, a monocolor point cloud is obtained. That would be the upper right image. This is one of the visualization modalities that is presented to the user during the experiment. The RGB image stream can then be used to construct a color point cloud by associating each point of the monocolor point cloud with a corresponding pixel in the RGBD image. The result would be the lower right image. An experiment was designed to investigate the effect of visualization parameters on the participants' performance and VR experience. The experiment involved the assembly of a puzzle consisting of 5 parts while immersed in a VR environment. The assembly task was chosen to be straightforward to minimize the advantage from personal experience. Figure 1 on the left is an example start setting of the unassembled puzzle pieces, and Figure 2 on the right is the puzzle after assembled. Each participant were asked to perform the assembly task 9 times, each with different puzzle starting position and a random visualization setting. Within the user's VR scenes, the pieces of the puzzle are stationary on a static surface. Both the camera and the VR headset positions are localized based on the puzzle's position. In the first 3 settings, the image stream with both color and depth images was displayed to the user. Each of these settings had a different image resolutions and frame rates. The other 6 settings visualize data as point clouds. Among these, 3 settings present monocolor point cloud, the other 3 present color point cloud. all with varied density and frame rates. After each trial, the researchers record the participants' completion time and request participants to provide responses to record and evaluate their subjective cognitive workload. The three statements which were utilized to evaluate the participants' subjective cognitive workload are presented on the screen. Figure 3A, which is the leftmost figure, shows the completion time of the participants. Figure 3B, C, and D, which is the second to the fourth box plot from left to right, show the responses from the participants on the Likert scales towards the three statements. Four figures in setting 1 to 3, color and depth images were displayed to the participants. In setting 4 to 6, monocolor point cloud were displayed, and in setting 7 to 9, color point cloud were displayed. The experimental results indicate that RGB and depth image streams are the preferred data visualization modalities. However, there are several factors that may confound the findings of the experiment. First of all, since only one camera was used during the experiment, the reconstructed point cloud could easily be occluded by the participant's hand on the surrounding object. Secondly, since the assembly task was straightforward and required little depth perceptions, the effect of the supplementary information provided by a point cloud is not significant. Furthermore, the point cloud frame rate is limited due to hardware limitations. Therefore, the image stream with a high frame rate and resolution is preferred by the user. On the other hand, observations of participants' performance and responses show that color was the perceptual enabler for point cloud data. Monocolor point clouds were reported to have little to no comprehensive visual feedback. Therefore, in most settings that visualize monocolor point cloud, participants report that they are more dependent on tactile feedback than visual feedback. This can be seen in the setting 4 to 6 of figures 3B, in which the lower score indicates the higher dependence on tactile feedback. In conclusion, this paper investigates the effect of variances in real-time VR-based sensor data visualizations on user performance in an assembly task. The variations include visualization modality, sensor resolution, data compressions, and frame rates. In addition to RGB and depth image streams, the VR-based system was shown to transfer color point clouds in real time. Future work will focus on investigating remote robot control tasks that require participants to solely rely on visual feedback. In addition, other visualization modalities, such as meshes, that can have both reduce the sparsity of the data and produce a more intuitive representations for VR-based control operations, will also be considered. That's the end of my presentation. Thank you for your attention.